Let's talk about geometric series. Now you can see these 3 bullet points that I have on the screen right now are all the things that we know about geometric series. The first is just what they look like. So if your series can be written in one of these forms, it counts as geometric. So this one right here is going to be our standby default way of writing them. So we'll start our index k at 1, and of course go to infinity. And we're adding up a number times a number to the k minus 1. We usually write them this way, and it's important to remember when there's no parentheses or grouping here, this k minus 1 exponent is only on the r number. The a is just a constant multiple on the outside, and in fact, you can factor the a all the way out of the series entirely. Instead of making k minus 1 the exponent and starting at k equals 1, see how this would make your first exponent 0 and then 1 and 2 and 3. What you could do is make the exponent k and then just have the index k start at 0. These two are both valid ways to write a geometric series. If you spell out the terms of either version, you get this. And then one perspective that I find occasionally really helpful is if you imagine factoring the a out of every single term here. They all have one a. So if you factor it out, then in parentheses, what's left is 1 plus your number, that is r, plus that number squared and cubed and so on. We have a formula for the nth partial sum of a geometric series. This is going to be the only type of series that has a formula for the partial sum in this. So this would be the sum of the first n terms. Notice that this is the 0 exponent to the 1 to the 2 to the 3, and then the last exponent you'll see in the sum is n minus 1. Okay, so our formula for that is a times 1 minus r to the n over 1 minus r. If r is negative, then the negative number shows up in both of these places. And then from this formula, we can see that as n gets very, very large, and we kind of compute the whole series, as long as r is a fraction, this part shrinks away to 0, and what's left is a over 1 minus r. So we have the rule that the series will converge if the absolute value of r is less than 1, so that this part goes to 0. In that case, this is the formula for your sum. And then if the absolute value of r is 1 or higher, then your geometric series is divergent. Let's look at a couple of examples. My first example here fits exactly the structure of this first type here. From looking at the setup, we can see the a value is 2/3, the r value is 1/5. Because 1/5 has an absolute value less than 1, we automatically know without doing any work that this is a convergent series. The follow-up question here is compute the actual value of the sum. So I'm going to use this a over 1 minus r formula with this a and this r. So the total sum, 1 to infinity of 2/3, 1/5, so the same. This one equals. So I'm going to have a, which is 2/3, divided by 1 minus the r value, which is 1/5. This is annoying by hand, but it's doable. 1 minus a fifth is 4/5. So this is 2/3 divided by 4/5. That's 2/3 times 5/4. We can do a little bit of canceling here, and I get 5/6 as the total. So if you could add up these numbers forever and ever and ever, they would total to exactly 5/6. This next example starts the index k at 0, but then the exponent on the r value switches to k. So over here, the first exponent on this is 0, and then 1 and 2 and 3. And then same thing is happening here. The first exponent is 0, and then 1 and 2 and 3. If we really wanted to, we could switch this to a k minus 1 and a 1 here, and it would be still the exact same series. In this case, the a value is 1 because there just isn't a number out here, and the r value is -7/6. Anytime we're plugging r into one of these formulas, it's going to matter if it was negative or not, so we do want to keep the sign on the number. Because this r value has an absolute value greater than 1, we can tell that this is a divergent series. So that means that the formula for the full sum here just doesn't apply. This is just divergent. But the partial sum formula does still work. That's true for every geometric series. So for example, we could compute S3, which is the sum of the 0 term, the 1, and the 2. So that would be, I'm gonna try to keep that formula on the screen as well. So A times 1 minus R to the n, A times 1 minus R to the n over 1 minus R. I'm going to leave this unsimplified because these numbers are especially gross, but whatever this actually computes to would be your third partials. I want to end this video with two kind of annoying examples. Sometimes a geometric series is given just as the simplified terms of the series. And you could still be asked the same questions, you know, is this convergent or divergent, compute, you know, the full sum or the partial sum. All those questions, you need to know what the A and the R value are, and it's not immediately apparent when they're given this way. So here's what you're going to do that works every time. You're going to factor out the first term from the whole sum. So in this one, I'm going to factor 4 out of everybody and just say 4, big giant set of parentheses. And over here, it's going to be 3/2, giant set of parentheses, and we'll see what's left. Writing it this way is going to help us see it like this. So then the number sitting out front is your A, and you should see 1 plus a number plus that number squared and cubed. So this number right here will be the R value, and this works every time, even when the numbers are really, really gross. So here, 4 divided by 4 is 1. 2 divided by that 4 is 10. 1 divided by 4 is 4. And I might go one more just to double check. I can tell that the R value is 1/2, but feasibly this question could have started like, is this a geometric series at all? In which case I really want to be sure these are all powers of 1/2. So if I go one more, I would have 1/2 divided by 4, which is 1/2 times 1/4. That gives me an 1/8. So I have a lot of assurance here that these are all powers of 1/2. So I can tell from looking at this that my A is 4 and my R is positive 1/2. So I could conclude from that information that this is a geometric series. It's a convergent one because the R value has an absolute value less than 1. And I could feasibly compute the total sum here if I wanted to actually add up this infinite list of numbers. I could plug these into A over 1 minus R. So A over 1 minus R, 4 over 1/2 is 8. So those numbers add all the way up to 8. All right, let's do the same thing for this more awkward list of numbers in my last example. We said the one trick is to always factor out the first term. The first term here is 3/2. So I can see right away the A value is 3/2. But then everything else is a little bit less clear. It's not even necessarily clear that this is a geometric series that we're looking at, but it is. Okay, so in this step, I want to write each of these numbers divided by 3/2. And that computation is actually going to take some scratch work. One thing I'll remind you of is that divided by 3/2 is the same as times 2/3. So I'm going to imagine each of these numbers times 2/3. And that's going to help us compute these numbers as we go. Okay, so 3/2 times 2/3 gives us the 1 that we're expecting here. And then we have a minus sign. 1/2 times 2/3 is 1/3. 1/6 times 2/3, we get 1 with a little bit of cancellation, right? 1/18 times 2/3, we'll get 1 over 3 times 9, that's 1 over 27. And now that we see it kind of organized, we're recognizing powers of negative 1/3 here, right? So this whole piece is my R value, so negative 1/3. I can see that it is consecutive powers of -1/3. So if I was checking that this was geometric, I would say yes, it is. If the numbers after the 1 1/3 were not, it was 1/9, 1/27, if it was something else, I would say it's not geometric. And then I can also see that the A value is 3 times. So again, we can tell this is geometric, we can tell it's convergent because this R value, its absolute value is less than 1, and we could compute the sum of this one as well, doing A over 1 minus R. Notice that the R being negative is really important right here because I'm doing minus a -1/3, which is actually addition. So this is 3/2. So this is 1 plus 1/3. That's 4/3. So I have 3 halves times 3 fourths. Just writing the reciprocal of the denominator. And I get 9/8 as my material.